Okay, so what we're going to do here is we're going to start with a circle. Slide this over here. Let's just make a circle here. And I think I'm going to hide point B for a minute. I'm going to place a couple of points on the circle. I don't want it to be B because I want to be able to move them and not adjust the circle's size. And B will make the size change. Now I'm going to draw the radii there, and what I'm creating again, as you know from your study of circles, is that what we're creating here is we are creating an inscribed, or a central angle rather, a central angle. And this arc right here, this arc CD from here to there, represents, this minor arc represents the same measure as this inscribed angle, right? So this is a 51.2 degree central angle, which is also a 51.2 degree arc. I mean, if you think about it, the arc could go just like the central angle. It could go all the way around and become a 360 degree arc in theory, right? So, okay, I have a central angle and an arc. This measures 55.99 degrees. So now what my question is how long is arc CD? How long is arc CD? Well, let's say I set this, I don't know, let's find a nice even number we can divide this by. Oh, let's set it to 60. Okay, well, I'm not going to get it to exactly 60. We'll get it right there. That's close enough, 60.23. So the question is, how long is this? Well, let's remember, okay, let's remember what we know about the distance around a circle, right? So the distance around a circle is equal to the circumference, right? That's what we call it, which is equal to 2 times pi times the radius, 2 pi r. 2 times pi times the radius. So in this case, I've got my radius defined here as 2.75. So I'm going to go 2 times pi times 2.75. That would be my total circumference, is equal to my total circumference for this circle. Or any circle with a radius, or any circle with a radius of 2.75, right? Now, what part of that circle is in the arc? Well, it's a portion, right? There are how many degrees are in a circle? That's 360. But how many degrees are in our arc? Not all 360 of them, only 60.23 degrees. So what part of the circumference is in our arc? Well, that part or portion or ratio is 60.23 of 360. So let's look at this for a second. This is the part out of the total. So we're writing a fraction here because this represents, one part that we have out of a total part that exists. So if we want to know if the full length, if the full length is equal to 2 times pi times 2.75, then the arc length is equal to 2 times pi times 2.75 times 60.23 over 360. Okay, that's all we're going to do. Okay, let me get my calculator and show you how that's worked out. So I've got 2 times pi times r times the the measure of the degrees in the arc or central angle, they have a degree measure that's the same, divided by 360. So this is the portion, this represents the portion of the circle that the arc represents. It's 60.23 parts out of 360. Right? And this is just the full circumference. So full circumference times the ratio that represents the arc. Does that make sense to you? I hope so. Okay, let's go back and check it. My answer says 2.89083. Let's try and hit OK here. We're going to put that line of questioning there for a minute. Let's use this circular arc tool. 1, 2, 3. Oh, I went backwards. Let me undo that. Here we go, the circular arc tool. 1, there's the center. Here are the points on the arc, or on the circle, that represents the arc. So arc D, we have over here, it's 2.89 in length, which is exactly what we'd calculated, 2.89, and then of course 0.83. Have to round because we have pi involved here. We don't have exact numbers. Pi is a little bit irrational, as you might remember. But you know, I can now take and adjust this, and all I need to do to calculate the new length of D is change this part of the formula. So let's go back up here. Sorry, bring that down. And my new arc length, if I take away 60.23, it now represents what part? 137.73. So I put 137.73 and I hit enter. And now I have an arc length. This is the arc measure, which is given in degrees, but the arc length is 6.61. And we come over here. Where is D now? Yeah, it says 6.6. We know it's 6.61. Well, it's provided that this is not being rounded. This might be 137.726 or something. That could throw it off just a little bit, okay? But basically, you get the idea. Okay, to measure that arc, we just multiply the full formula for the circumference by the ratio that's represented by the arc. In this case, 137.73. Let's do one more, and we'll see it here. How about 311.72? So we'll bring this down, and then we will multiply by 311.72 out of 360. And we have 14.96. And this one measures 14.94. Okay, we're off a little bit. What is making us off is the idea that this angle is not precise. We also know that the length of this radius may not be precise. Okay, but it's getting us very close. It's doing a pretty darn good job. These numbers are exact. These numbers are exact because it knows the true value of D. It knows the true value of A, and it knows the true value of the angle or of the arc measure. So it's able to calculate precisely the length of D, whereas we're using rounded numbers when we use our calculator here. This is rounded to 2.75, and this is rounded to 311.72. Okay, that gives you the idea of how you can calculate that. Now, let's think about for a minute. I want you to think about a dilated circle. So I want you to watch this. Ready? Let's dilate a circle. Here we go. I'm going to take our circle, dilate our circle from this point, and let's give it a new, let's multiply it by a ratio. Let's give it a radius of 5 over 2.75. So if this is new over old, and the old was 2.75, that's not exact, but pretty close. The new is 5. The new radius should be 5. Okay, and then if I construct, let me make some rays here, through there and through there, and let me go ahead and find my intersection points here from the ray and the circle, and this ray and the circle, and then let's hide the rays. So we're going to hide those babies, and then we're going to draw our segments from A to F, A to F. Okay, now what would the length of this 79.56. Ooh, we didn't figure out the length of the 79.56. So we're going to use this. I'm going to slide this out of the way. Hopefully by now you've recorded it. And if not, you can go back and watch what we've done before. So what was the length of arc D here? Well, arc D was equal to, we used our formula, 2 pi r, where r was 2.75, right? Times 79.56. Let's put that in. So we have times, we're going to go 79.56 over 360. So we have this being 3.81. Okay, and there it is, 3.81. So what about arc EF? Well, what else needs to be changed? First of all, the angle is exactly the same, right? The angle is 79.56, and we constructed to make sure we are still at 79.56. But the radius has changed. Now the radius, oh, I wanted it at 5. You could tell there was some rounding going on because we're actually at 4.99. So we're going to have to change this part of the formula. And instead of having a radius of 2.75, we're going to change it to 4.99. So now we have 6.92903. Let's make sure that that's correct. We'll use our circular arc. Give me arc FE. We have K, and it's 6.93, which was basically where we're at, 6.929, right? So there we have it. Our formula works, but now I want to see something a little more interesting. Let's try writing the ratio. Let's put 6.2. Ready? Let's try writing this ratio. I want you to see this. Control divide. Let's put the ratio of the arc over the radius. So we go 6.9. Actually, you know what? Let me do it this way. I'm going to go up here and just copy that value and paste it down. There it goes. Very, very precise. And, oh, we'll just put it over 0.99. We get 1.38858. That's sure interesting. Let's get back to that in just a minute here. What about when we did the same measured angle? But in this case, let's come down here. Hold on. Control divide. Let's write our ratio with that measure over 2.75. Remember, we used 2.75 for that radius. 1.38858. So there is a constant here. There is a constant. That is the ratio of the arc to its radius remains constant. The ratio of the arc to its radius. Why would that be? Let me just have you think about that. How did we create this circle here? Well, we just created it. How did we create that circle there? What transformation did we use? Remember, let me put this in here. Remember, the second circle was created by dilation. Remember, dilations preserve angle measurements, and remember, dilations preserve proportionality. Oh man, those are good things to keep in mind, right? They preserve angle measurement and they preserve proportionality. So the proportions, the ratios of D, arc D or arc CD here to AC is going to be preserved from EF to AE. In other words, this ratio, measure of EF over measure of EA, is going to be an equivalent ratio as measure of arc CD to ray or to segment CA. those ratios are equivalent ratios. Okay, and now we'll think about this a little bit more. What if I had a 360-degree arc? Let's go back and think about this. Let's go up here and let's explore a little with our calculator. Is it going to turn on for me? Oh man, maybe my calculator's dead. Hold on, let me switch it out. Okay, so now we have here, I want you to look at this line here. I'm taking the formula 2 times pi times r, which is my formula for the area of the circumference of a circle, and I'm timesing it by an arc that measures the entire circle, 360 degrees out of 360 degrees. And what happens is 360 divided by 360 is 1. So I just get, then that would measure of that length of that arc would be 2 pi r because it is a full circle. What if it was a half a circle, 180 degrees divided by 360? Well, then it would be pi r. What if it was 90 degrees, right? What if it was 90 degrees? Well, then it would be pi r over 2. So now I want you to go back and think about this. Remember how we said that all circles are similar? All circles are just some dilation from one to another? And we proved that? So what if we took and recognizing that there's some constant between these? In other words, the relationship from the arc to its radius remains constant, true to its angle measure, right? So that whatever angle measure I plug in here, it's always going to be proportional to the radius is the length of the arc, right? It always depends on this radius, right? What if the radius was 1? Okay, so let's try that. Let's go define the r equals 1. So if our radius of our circle was 1, well then a arc of an entire circle would just measure 2 pi units. An arc of a half a circle would measure pi, and the arc of a quarter circle, or 90 degrees, would measure pi over 2. What we have here, guys, these are angle measurements, right? 90 out of 360 that are measured in degrees. These are angle measurements that correspond to 90 degrees out of 360, but they're given in terms of what we call radian measurements. Radian measurements. So we take this and we multiply it by the radian, and we get the length, or the radius, then we multiply this times whatever the radius is, and we get the length of the arc that has a radius of whatever we just described. Okay? Let's try this. So if I took, this measure, and let's say I had a circle with a radius of 4, I go times 4, then my answer would be that arc would be about 6.28319. So let's try that. Let's go back to our GeoGebra real quick. I'm not going to save that. We're going to draw a segment with a given length. The length is going to be 4. We're going to construct a circle, right? We're going to make a perpendicular line that goes through here and A, okay? I know that line. Oh, I don't know this line. I don't know if this is parallel. Oof, I should have thought about that. That line, oh yeah, that line is parallel. It was constructed parallel for me. I can see the slope is 0. And I can prove it by, measuring the point, but let me just go ahead and find this angle here. So we'll measure this angle here, be you see it's a right angle, okay. So this is a 90-degree angle. The unit length of the radius was 4, and we said a 90-degree angle had a radian measurement of pi over 2, which meant that pi over 2 times the radius of 4 is going to give us a length of 6.28319. So let us measure that now. Here we go. We're going to measure this arc. And we get 6.28. So this is what radian measures are. Radian measures are substitutions for degree measures. Okay, it's another way to measure angles. Okay, a full 360 degrees is measured as 2 pi radians. 180 degrees is pi radians, right? Because half of 2 pi, right? And then 90 degrees is pi over 2. 45 would be pi over 4, etc. Okay, so that's your introduction to radian measurement.